Hi everyone, I think it is recording. So let's start today's class. So I hope it is audible as well. My voice is audible as well, and my screen is also visible. So let's start today's class. Uh, so let me begin with what we have done in the previous class. So what we have seen, we have seen that actually we are after so let's clear out what is our motivation in these few lectures throughout these few lectures, which is that we are going to prove that theoretically what we have seen numerically in the case of this logistic equation, that sometimes the behavior of this behavior of the logistic equation could be very chaotic, and what does this means in terms of rigorous mathematics, and whether or not it satisfied the definition of the chaos what is already there, and due to the definite definition of the chaos. First of all, the sensitive dependence, we want to prove mathematically that the logistic equation for the parameter value equal to 4, it is sensitively dependent to the all initial condition, and then there is a transitivity, and that it also contains the dense periodic orbit. So, and we have seen that we could from our previous classes, we actually have seen that from the structure of the map we can actually infer so many things about the definition of the behavior of that map. So basically I'm saying that we can know about what is the um, um, is there any fixed point or not, is there any periodic orbit or not, or they are stable or not, that we can tell from the only the structure of the map. And that's why we are after this graphical composition, and we have seen that we have defined some kind of wiggly turrets. And what does this spike means? This spike means that in a very smaller interval the map increase rapidly, it has a sharp increase, and in attain a maximum value then actually decrease. So there is a steepness in the curve, and in this class we want to see that why this steepness is actually related to the sensitive dependence of the initial conditions. So let's begin. Today we are going to mathematize the concept, actually the sensitive dependence of initial condition. Sensitive dependence. Okay, let's then begin with. So let me first talk you about what does we mean by this sensitive dependence. We have already idea what does this sensitive dependence means in, but let me begin with another thing that we have already seen what actually we are meaning by sensitive dependence. So when a difference equation is used to model a real world problem, the particular solution of interest is specified by an initial condition, and we given that initial condition we write some code, and we given that initial condition to the computer. Now the question is, if we actually model the real world problem by this difference equation, then what is our goal? So our goal is to predict the future, and that means if I put the initial condition what is actually I am observing in the nature, then I should get actual future of that system in the near future. Now what happens in the reality, there could be, we cannot give exact precise initial condition to the computer. Why? There are two error could be there. One of them is the measuring the measuring instrument error, measuring instruments error. That is, I have a measuring instrument and that has a finite precision, so because of that we got an error. We can have an error in the initial condition, and second thing is that the precision up to which the precision up to which we can give with the precision up to which a computer accepts the number. Computer accepts the number. So suppose that computer accepts a decimal number and it takes the value. So there are suppose that there are 64. It actually only support only the 64 values after a decimal. So then you cannot put a large since we know that if suppose our irrational number, it cannot be contained in the 64 values. Actually irrational number means there are infinite actually after decimal there are infinite digits are there. So any irrational number cannot be exactly given in as an input in the computer. So there are two errors are there, and due to this error we have to make sure that whether or not our predicted future is actually remain closely nearby to what we are predicting or not. So so that's why comes the concept of sensitive dependence of initial conditions. So if we can ensure that, suppose if we ensure that there are two initial conditions are there. Suppose x0 is the real condition and y0 is our that approximated value that we give input as an input in the computer as initial condition. Now we are using this y0, we are predicting some future. Now if this future remains very close to x0, then we will say that our system does not have any sensitive dependence of the initial condition, and we can perfectly predict the future of the system. And if there is in the system there is a sensitive dependence of the initial condition, okay, there is a sensitive dependence of the initial condition, then what we have to do that then we can actually we cannot have the prediction. So that is called chaotic in nature. So today we are going to see in terms of mathematics how you actually define this sensitive dependence. So first begin with some computer code. So let me show you how this actually happens for a logistic equation for mu equal to 4. So I am going to show you that how this logistic equation that if we start from very nearby initial condition, how with as time pass on, these two initial conditions actually the orbit of these two initial conditions differ from each other, and how fast it actually differ, it depends on the how closely we started. So terminal. Okay. So let me open this code where I have written. So it's very simple code. So let's start from there are two initial conditions upon 0.2 and 0.21, and what I am doing, I am only noted down the 30 iterations, and I am iterating these two initial conditions, and I will plot these two. So let's see what we see in the what we see. Actually, you can see that at the beginning they remain very close to each other. So this dotted line is the for x2, and this so let me do it one thing, then it will be very clear. So first let me trajectory 1 and trajectory 2. Now let's see. Yeah, now you can see that this is trajectory 1 and trajectory 2 remain very close to each other. Basically these trajectory 1s is generated by using the x1 initial condition, and the trajectory 2 is actually generated by using the initial condition x2. And you can see that these initial conditions are close to each other. So how close? They are 0.01 apart. So one is 0.2, one is 0.21, and you see they remain close to each other for very for only the first time period. Then actually they differ from each other, and that is this trend is going on, and after some time you cannot predict. Suppose your initial condition is x1 and actual real world initial condition is x2, and you cannot predict if you have that much that much accuracy in your error in this accuracy in your measuring instrument. Then what you will find that you cannot predict the actual future from the what you are actually measuring from there. You can see there at future the prediction, if you give prediction from by using x1 and your actual initial condition is x2, then your prediction will fail miserably. So now let's start. So will it be good enough if I go nearer this point? Suppose we go nearer 0.001. So this is much more closer. What it will happen? Let's see that yes, indeed they remain very close. Actually they are overlapping here 1 2 3 4 5 6 7 8 until 8 iteration they remain very close, and after 10 iteration they start to deviate from each other, and after some time you will see that they actually deviate, these two initial condition deviate much more. So that means if we start from nearer to that initial condition, it stay closer for a longer time, then it actually diverge. So here for the case you can only predict safely for n equal to 8, means for 8 time period you can predict the thing. Now let's go to more closely. Suppose 2 so 2000001, so that much close. If we go that much close, so what it will say? So but you cannot predict much more than that. Okay, yeah, you see that yes indeed it actually very close, but after near about 13 or 14 it start to deviating, and from then it actually deviating very largely, and you see the prediction is lost. So that is actually there. So when you are starting from very close, they remain close after some time, and you can predict only that much, and after that the long term actually the thing is the long term prediction has been lost, because that system has a sensitive dependence on the initial conditions. So let me do one thing. So let's see that the difference between that thing. So it's very fun to see in the computer. So let's see, not plotting these, but let's see plot the difference x. Suppose difference suppose x difference equal to Now x difference is equal to or maybe xd equal to, maybe here you can write absolute of x1 values minus x1 values minus x2 values. I want to write that. And plot that things. Okay, let's see. As it is showing. So let's start from point 2 1. Start from point 2 1. You will see that the difference between that initial condition actually start diverging from very fast iteration. Now let's see for the second case, that is the case 0.001. You will see that they actually remain close to 0. So they remain close to 0 after 5-6 times. Then 5-6 times, 5-6 iteration. After that it actually diverging, it's start to diverge very large, and that is actually happening there. Now let's see for that case, and we expect it remain close up to 15, then it actually start to deviating very large. So that is actually happening here. So from here we actually get an idea what does this definition of the how we can define the sensitive dependence of the initial conditions. So let's start with, so we'll now go towards the definition. Definition, let's go towards the definition. So suppose, so there are, suppose, let me draw it. Suppose we start from two very initial condition, one is x0, one is y0, and the iterates are look like these, similarly here also these, and these, so these are the iterates of for the x0. And these are the iterates for so sometimes it get close to this trajectory, and not trajectory, these points. So these points are very close, you can see. Sometimes it get close to each other, and sometimes it actually become very far from each other. And one thing you have to remember, that these distance, suppose these maps actually map the interval 0 comma 1 onto the 0 comma 1. Then suppose f is a map, then the distance between these 2 points cannot be far away from 1. The maximum distance between any 2 points can be 1, because after that it actually become outside of the region. Now here you can see that x0 and y0, they sometimes get closer, come close to each other, and sometimes it become far apart from each other. Now suppose this is delta. So if there are suppose there is a open interval I, so this, suppose from this red line is an open interval name I from here to here. And how in mathematics we define the sensitivity? We say that if there are two initial conditions, they are very close to each other, and if we found that after some iteration they move away from each other, delta amount, this delta far away, or some other fixed distance far away after any iteration, and they separated at least by this delta distance, then we will say this is the sensitive dependence of initial condition. And if we if we decrease the length of this closed interval, suppose here to here, if in decrease from suppose here to here, then you will see when we will decrease this open interval, the x0 and y0, if I take the x0 is fixed, now the y0 from which I am taking from y0 is the point, if I iterate, after n iterate, it becomes delta distance apart from each other. And when this if I choose that open interval very smaller, then you will find that x0 and y0 become very close to each other. Now let's define formally what does it mean. So a map a map if 0 comma 1 map into 0 comma 1 has sensitive dependence of dependence at some point at point x0. Suppose this is a map, and I am saying that this x0 has a sensitive dependence, then has a sensitive dependence at a point x, if the map, if the following condition, actually the following conditions hold. Following condition holds for some delta greater than 0. So for each open interval in 0 comma 1 I containing the point, this point x0, there exists a y which is belongs to I. So you will find that you will for every open interval which contains this point x0, you have there will be a y such uh, that there will be an y, there will be a y and a n such that fn x minus fn actually x0 minus fn this is y0, suppose this y0 become greater than equal to delta. So you will find that, so sensitive dependence means there will be exist some constant delta and obviously this delta will be less than 1 if this map and this delta less than will be 1, less than equal to 1. So you will there will be means for delta there will be, so if I want to find that whether or not this x0 has some sensitive dependence of the sensitive dependence or not, then what you have to what you have to check that in suppose that there is an open interval, suppose that x0 is value, suppose x0 is 0.25. so what you will say, suppose we will take a open interval like 0.2 to 0.3 which contains this point. So between this 0.2 and 0.3 you will find that 0.5, and what you have to check that between this 0.2 and 0.3, or this is only one open interval, and for every interval which contains this x0 you always have to find, if you can find a y in between these two, which is means, and also find an n, and if you iterate this x0 and both y0 n times, what you will find that the difference between this future of this x0 and the future of the y0 actually far apart from this delta, far apart at least the constant delta. That's why it's called the sensitive dependence of the initial conditions. So in words, so in mathematics, instead of word they use the quantifier. So let me introduce this quantifier. So don't worry, nothing new here, only these definition in terms of mathematical symbol. So how to read it, because writing this much language is very difficult. So let's introduce these symbols. So this definition, it's written in terms of this. So first let us, these symbols means abbreviation for all. These means there exist or there is, and there is these symbols means, so suppose x, these symbols means x belongs to I, and this symbol means that I contains x. So this means here x is given, so x is given, so x belongs to I, so here I is given, so x is a number which belongs to x. So fine, here I is given, the interval is given, and x is a number which belongs to I. Here I, not I given, here x has been given to you, but I is that any interval which actually contains the x. So using this quantifier, how you can write this definition? So it written as there exists a delta which actually greater than 0, and for all open interval I which actually contain x, open interval I which contain the condition at which I am going to check the sensitivity. So a contain initial conditions, and there exist a y which belongs to this interval I, or this open interval I, and there exists a n which obviously belongs to a natural number, such that the after nth iteration you will find that fn and fny is at least delta away from each other. This is called the sensitivity at, this is called sensitivity, and that's how it is read, sensitive at x. F is sensitive at x. Now what does mean the sensitivity at everywhere? Now in case of it is for only particular x. Now in case of the logistic map you will find that it is actually sensitive at every point. So sensitivity at everywhere means the chaos, but you will find that the sensitivity only one point does not mean chaos. So in the next example I will show you. So one example of this sensitivity. So let us make clear here that how to, by the using definition, so how to prove sensitivity using the definition. Okay, so we'll so it here. Okay, okay, to prove the definition, to prove from the definition f is sensitive at x. So first of all let me write it. To prove from the definition that f is sensitive at x, you must choose a constant delta. So first of all one has to choose a constant delta which is actually greater than 0, which is greater than 0, such that, so first work is you have to choose that constant delta such that for each open interval I which contains x, there is a y which belongs to I. You will find that you will find an n, you will find an integer n, that f to the power n x minus f to the power y is greater than equal to delta. So the proof step will be, the step of the proof will be choosing a number, delta greater than 0, and second verifying choosing a number delta greater than 0 and verifying that the chosen delta works, that chosen delta satisfy this. So here the by proving these things, means for proving these things, the main hard work is finding out this delta. So what you have to do, you have to explore the multiple delta and you have to see which delta works. That's all. So let's see an example of the sensitive dependence of the initial sensitivity. So one example is so that the mapping f 0 1 to 0 1 with fx equal to x square as sensitivity at x equal to 1, sensitive dependence at x equal to 1. So what we have to do, we have to find first this delta. We have to find a delta greater than 0, for which that these we have to find delta and a y, and in every open interval which contains this x equal to 1, we have to show that fn1 minus fny is greater than equal to delta. So let me first show two things. First, fn1 means what? So fn1 means, so let me check this way, what does this means? So at x0, if I start from x equal to 1, so for x it will be remain 1, and if it f square also remain 1, f cube also remain 1, and it remain 1 only. So that means f n also be fn1 will be also be 1, and for suppose any other value of y, and it actually map from 0 to 1, okay, for any other value of y, so it will be f will be y, then f will be actually y square, first y, then the in y square, then y to the power 4, then y to the power n, and it goes on. So if we plot these two, so the iterate will look like, so suppose this is the iteration, so 0 1 2 3 5 6 7, so like, and this is 1 suppose. So you'll find that 1 for this is x equal to 1, and suppose this is some y, so you'll find that any x equal to 1 will remain 1 at everywhere, but y equal to 1 you will see that they actually start falling away, means because it's y square, y to the power 4, so it actually approaching to 0, it will approach to 0 like this, so it will approach 0 like this. So that will any y, actually that many dot will not be there, so let me put it dot this way, these this way, actually it will fall apart from each other, x equal to 1, and suppose it's any y, and since, and you see that since this y actually remain in between 0 to 1, in between 0 to 1, that means y to the power 2 to the power n, which is actually here. So it is, you can write fn equal to will be y to the power 2 to the power 1 n actually. So is goes to 0 as n tends to infinity. We know that if this is, since this is a fractional number, so as we increase n, this 2 to the power will be increasing, and if the power increases, the number will be decreases, and we have seen that, and it actually goes to 0. Now that's why I am showing that it it came at n goes to 0, it actually these the iterates of y actually came closer to this horizontal line. So that means, suppose, so let me first choose an delta equal to half. So for delta equal to half, what condition he has to satisfy? So for delta equal to half, so this is actually 1. So first let me mod 1 minus y to the power 2 to the power n should be greater than equal to delta. So delta is half. So if I take delta is half, so that means 1 minus something which have to be greater than half. So that means y to the power n, if it become less than half, then the above condition will be automatically satisfied. If y 2 to the power n, so if y 2 to the power n less than half, then it will be automatically means that 1 minus y to the power 2 to the power n will be greater than delta or half. So we have to say that we will actually find one y, which actually after we have to find an n that so some y this will be satisfied. So that means we have to find a y such that so we have to find a y, so in any interval. So if we can find, so if I choose any interval, suppose this is, so if I choose this is 1, so if I choose these to this interval, or these to this interval, or these to this interval, these to this interval, or these to this interval, or maybe whole this 0 to 1 interval, it doesn't matter. But if I choose any interval, I will get an y such that y 2 to the power n will be half. These actually satisfied, we will find some n for which this actually happens, because we know as n tends to infinity, since y is a fractional number, it less than 1 actually, it less than 1 and it remain between 0 to 1. So that means as n goes to infinity, it actually goes to 0. So somewhere in between there is a number half. So you will always find a n, suppose this n, actually you actually find this n here for this case. If this is n x equal to half, so you'll found an n, suppose this is n equal to 8 or 9. So you'll find an n for which the nth iterate, that means this is the f of 8 of y, or equal to 2 to the power 2 to the y to the power 2 to the power 8. So you'll find that the after 8th iterate, the y become lesser than half. So you will always find a y which will become after some n, and you will find also an n for which this y to the power 2 to the power n, or basically it does mean that f of n of y is less than half. So for any interval which contain x equal to 1, you will always find a y. There will be always a y, and for which you will find a n which satisfied this satisfied that the sensitivity conditions. That means, so you will always find f to the power n 1 minus, you will find always a y for every interval which contains 1, which will be greater than delta. So that means that thus it says the f is sensitive at x equal to 1. This is the thing, and this is true because this function as n tends to infinity, this fn actually goes to 0. So that's why, and f1 remains 1. So that's why this actually satisfied, otherwise it can't be satisfied. Now this is how one proves the sensitivity at any point. Now let's move by another thing. It is called the negation. So let me introduce. Now this is only, but to understand a mathematical concept, we sometimes have to see in other way around. That means we have seen that what does this sensitivity means, but we don't know what does mean that a point is not sensitive at all. So if you understand what does that mean, that a point is not sensitive at all, that means the opposite of these, then it is easy to understand why I am saying there is the sensitivity at this point. So the formal procedure, it is called negation statement. Negation. So the formal procedure is 1. So formal procedure is so first turn all there exist symbols to for all symbols and vice versa, and then replace the inequality in equality fn y minus fn x by its negation, by its negation, by its negation. This gives if we do, then it will give, this gives that. So first let me go there. So let me first of all write the definition, then I will do. So first of all, definition of sensitivity. Let me write the definition of sensitivity. So definition of sensitivity is there exists. So definition, there exists a delta which is greater than 0 for all I which contain x. There exists y which belongs to y. There exists n which belongs to natural number, obviously. For that, fn x minus fn y greater than delta. Now this is the thing. Now let's make this statement negation. So by what we'll do, so we'll replace this symbol by for all. So this will see read as for all delta greater than 0 there exists an I which contains x for all y which belongs to I and for all iterates belongs to the natural number. The distance between this fn x and fn y will remain smaller than the constant delta. Now you see that this is the sensitivity, because you see that for every y and for every n they will remain close to delta, and what there will exist a I, so there will means within, so you can think that this I is the means accuracy limit. So within this error range, so if you can, so if your exact value is real value is 0.1 and you can predict that means only that it is 0.10001, so this 00001 means this interval. So if you find an interval and if there is a point within this interval, and if you start from that point, y means within, so suppose you have a point, so let me give an example properly, then it will be clearer. So suppose there is a point 0.1 and here is a point 0.9999 and here is a point 9995 and here 0.010001. So suppose this is, I find a interval I, and if I choose any point, from this interval, and if I choose means suppose my real actual world value is 0.1 and my measuring instrument tells me some value between these two here. Now since we know that whether you choose this value or any other value, for all iteration these all iteration, the iteration of this 0.1 and the iteration of actual the measuring value will remain close to each other for all iteration. So that means from this y, this approximation value of x, we can actually predict this the future of this x, actually real world, the future of the real things. Then we will say that this actually not at all the sensitive to the initial condition. The future is not at all sensitive to the initial condition. There is a range within which, error range within which, if I give input to the computer, and it will ensure that the future will not be far away from what is actually happening. So that is called the that's how they define the negation, or this called that f is not sensitively, this is called f is not sensitive dependent at x. Okay, let me give an example. So an example, so prove that if map 0 to 1 to 0 to 1 with fx equal to half x does not have sensitive dependence at 0. So we have to do that for all delta. So let's some delta is greater than 0 to show that that for some open interval, to show that for some open interval 0 1 contain 0 for every y belongs to y and every n, for every y belongs to y and for every n. So in this interval f to the power n y minus fn 0 is less than delta. And so that means we know that fn 0 means 0. If we put x equal to 0, that will be 0 for everything. Now that means we have to find that fn y is less than delta. So what we have to find? So here in the similar to the previous case, here we don't have to find the delta, because for all delta it has to be satisfied. We have to find an interval. We have to find an interval for which for every y from that interval this condition satisfied, the above condition satisfied. Now if I draw these curves from here, you can actually suppose this is 0 to 1, this is 0 to 1. So this is y equal to f equal to x line. This will be the line, suppose this is line half, suppose here is half, so this will be half, maybe this will be f. Now what will be the f square? So let's find out. So f is half x. What will be f square x? That will be f of fx, so that will be half of fx, so half of x, so that will be 1/4 x. So it will be, so half of this, so somewhere between here, so this will be f square. Now again this will be half of this will be here f4, so actually f cube, and this will continue. So you find that all graphs that actually all graphs lies between this f. So that means f is always higher than the f square is always higher than the f cube, and this continues. So in general fn is less than f. So if we have to prove that fn is less than delta. Now if we can prove that f is less than delta, that will automatically satisfy this, because since f is actually greater than f to the power n, so if f is less than delta, the fn will be always less than delta. So we have to find an interval for which every y, for every n, this has to be satisfied. So that means we have to find that fy is less than delta. So let the interval, so this means delta, this is means half y less than delta, this means y has to be less than 2 delta. So if I take any interval between 0 to 2 delta, 0 to 2 delta for every y, so this actually give the definition of the open interval. So if I take the interval is 0 to 2 delta, then for every y in between this open range, actually then fy will become half of y, and that which actually become less than delta, and if f less than delta, the all higher iterate will be always less than delta. So actually we have find interval which is if I choose I between 0 to 2 delta, then for that if I take any point from that interval, and for every iteration n these conditions satisfied, that means f less than delta and f to the power n actually must be less than delta. So that means this says that, so if I take interval 0 to minimum of 2 delta and 1, and let n to then y belongs to I, y belongs to n, and n belongs to natural number, we know that f to the power n y minus f0, that will be half to the power n y, that will actually less than half y less than delta. So that's satisfied. So that means f doesn't have f have sensitivity at x equal to 0. So that's all. Now why at the first of the beginning of the class, why I have said that it is a direct connection to the spike, means that how steeply the curve rising or not, because of that thing. So let me plot this graph where the sensitive dependence is there. So suppose, so we know that at x equal to 1, f equal to x square has a sensitive dependence. So this is the identical line. So we know that as we increase the iterate, it will become x to the power 2 to the power n, and some suppose n, for n it will look like this. And you see that if you choose this is the open interval I, this is the open interval I which contain 1, then you see the iterate this, the f of x actually this 1, f of x actually f of 1 equal to 1, this value. But if we choose the fy here, suppose this is your y, so fn y will be actually this value here, fn y. Now you see the distance between these fn1 and fy. So it is very, the distance is very large. Although the distance between these x equal to 1 and y is very small, but the distance of the future after nth iteration, it becomes very high. Why? Because this has a very steeper slope at this point. So if it has the steepness, then very high steepness, then you will find that the map actually map actually takes the point far away from each other. So that's why if the system has a very steepness, then it will become sensitive dependence in the initial conditions. Now in the previous class, now you see that we have seen that it has a wiggly nature, and we seen that from the spike lemma that it has a spike like, it contains spike like structure, that any one hump map, and that actually tells that if the spike is everywhere in the region, then at the everywhere the system will be sensitively dependent. So that's all. So we'll in the next class we'll again come to this graphical interpretation why this sensitivity occurs, and then we'll go to jump to the proof of the sensitive dependence of the logistic equation. So that's all. So thank you. Now I am ending this class here.